In this video, we will discuss and illustrate the important notion of continuity of a function. We will talk about what can go wrong when discontinuities occur and how we can handle it. We will include examples when we can fix things using removable discontinuities. A function is said to be continuous if a graph can be drawn, at least in principle, without lifting your pen off the paper. For example, the straight line y equal x in this diagram was drawn without lifting the pen. The line, of course, goes on forever. So one has to imagine, in principle again, being able to draw as much as we like, back and forth as far as we like, without ever needing to lift the pen. In fact, this works for any graph of a linear function. Same is true also of the graph of y equal x squared, y equal sine x, y equal e to the x, and y equal to ln of x. They're all continuous functions that could be drawn without ever lifting your pen off the paper. When we imagine drawing without lifting our pen, there are no holes or gaps, and the limiting value precisely fill in where your pen is supposed to move to, captured by the statement, the limits of fx as x approaches a is the value of the function at a, namely f of a. And this has to work for every input x equal to a in the domain of the function. There are no surprise jumps or leaps, and you can think of any limiting behavior of the function as coinciding with the actual value of the function. There are two main obstructions to continuity in practice. Firstly, we must consider denominators of fractions. We're not allowed to divide by 0, and so we have to avoid values that cause the denominator of a fraction to be 0. The second main problem is when a function is defined piecewise, which means that there are two or more pieces, in the description of the rule for the function, leading to two or more pieces of the curve. Here's an example of a piecewise function that happens to be continuous. The modulus function, fx equal to the modulus of x. This function is defined in two pieces. If x is greater than or equal to 0, the function is equals to x, and it's equal to minus x if x is less than 0. The graph is well known to most of you. It's a V-shaped graph formed by taking the line y equals x in the first quadrant in the plane and combining it with y equals minus x in the second quadrant. The two pieces of the curve or the graph join up, matching perfectly at the origin. You can imagine drawing the V shape without lifting your pen off the paper. By contrast, consider the following example, which turns out to be discontinuous, by which we mean that we will be unable to draw the graph without lifting our pen off the paper. For this, we modify the previous example and consider the function with the rule fx equal to x over the modulus of x, which again can be described in pieces. When x is positive, the magnitude of x is itself. So dividing by x gives the value 1. When x is negative, the magnitude of x is minus x. So dividing x by minus x gives the value -1. The rule, however, is undefined for x equals 0. So this is what a graph will look like. Note that these two lines get arbitrarily close to the y-axis, but don't actually meet. You can think of there being two holes on the y-axis, and y equal 1 and y equal -1. It won't make the overall curve continuous by filling either of these holes. X approaching 0 from above, from the positive right-hand side, the y values are stuck at +1. So the limit from the right is +1. By contrast, for x approaching 0 from below, from the negative left-hand side, the y values are stuck at -1. So the limit for the left is -1. We have these contrasting one-sided limiting behaviors for x over the magnitude of x. We have a limit existing from the right, which is +1, and a limit existing from the left, which is -1. However, the overall two-sided limit does not exist, since these two one-sided limits are not equal. In other words, there's no hope of filling in the holes to make the curve continuous so that you can draw it without lifting your pen off the paper. Let us consider a few examples of rational functions. You'll recall that rational functions are ratios of polynomials of the form y equal fx equal px divided by qx, where px and qx are polynomials. Problematic behavior occurs when denominators become 0, often, but not always, leading to asymptotes. Consider the two contrasting examples of fx equal x squared -1 divided by x -1, and gx equal x squared -2 divided by x -1. Both of which will have 0 denominator if x equal 1. So that the input x equal 1 is problematic, but in quite different ways. We can produce the graph of f, which turns out to be a line with a hole at the point 1, 2. And the graph of G, which turns out to have an oblique asymptote and a vertical asymptote passing through the x-axis at x equal 1. In the case of the function f, the rule becomes fx equal x plus 1 for x not equal to 1, producing a line with just 1 point missing. If we fill in the hole, then we get the full continuous curve. And we can say that the discontinuity is removable. By contrast, if we look at the graph of G, no matter where we travel on the vertical asymptote corresponding to x equal 1, we cannot find an input that will join up to the two branches of the curve. They always remain separated. We can say that the discontinuity is not removable. Let us discuss another famous function that has a removable discontinuity. That function is fx equal sine x over x, with the domain the set of all non-zero real numbers. The rule is not defined for x equals 0 because x in the denominator would definitely be problematic. Here is the graph. Here is the graph. Because of the wavy periodic behavior of sine x, we expect the curve to undulate forever to the right and left. However, the amplitudes of the undulations decrease the further we are away from the origin. However, the amplitudes of the undulations decrease the further we are away from the origin as the denominator gets larger and larger. Multiplying by 1 on x has some kind of dampening effect on sine x. The graph also has perfect reflectional symmetry about the y-axis. It's an example of what we call an even function. As x approaches 0 from either side, y equals sine x over x approaches 1. Because the limit exists as x approaches 0, we can fill in the hole and then adjust the rule for the function, which remains sine x over x for non-zero x. But now take the value 1 in the special case when the input x is equal to 0. The discontinuity turns out to be removable, and we produce this beautiful, continuous, smooth curve. It's a famous curve that has many applications in areas of physics and engineering, such as signal analysis, acoustics, and optics. In this video, we considered an advanced discussion about limits in the context of continuity. We discussed the notion of a continuous function whose graph we may think of as being drawn without lifting the pen off the paper. This property can be defined in terms of limits, namely that the limiting behavior of the curve at any particular point actually takes the limiting value. We considered contrasting examples, some with a removable discontinuity at a particular point where the limit exists. And we considered the famous function fx equal sine x upon x. In cases where it's not possible to remove the discontinuity, we looked at examples such as where the left and right-handed limits exist but were not equal, and where there was a vertical asymptote for a rational function. Thank you very much for watching, and I look forward to seeing you again.